And we're going to talk in here about some challenges, uh, kind of define water resources sustainability, and I'll give you some examples of assessments and risk awareness approaches and tools. This lecture just basically scratches the surface, gives us an impetus on why we study water resources engineering. This is a great quote from Larry Mays' textbook that you have about what water resources sustainability is. I'll give you, you can have a few seconds here to read this, but essentially we're talking not only about humans, but also ecosystems. Without ecosystem health, we don't have good human health. If we look at the facets of sustainability, obviously we have the availability of fresh water supplies, be that either groundwater or surface water. We have the infrastructure to both convey that fresh water to the users, but also to protect when we have an overabundance of water, which would be in the form of flooding. We also have to have infrastructure to deal with wastewater. Obviously, if we allow our human waste or industrial waste to get out into that area where we're, into the supply that we're drinking from, that causes disease. We also have those institutions that manage water resources in terms of your regulatory kind of agencies or your resource agencies, like the Raleigh Municipal Utilities. They're the resource agency that provides the fresh drinking water for us here on the campus and for you living in your homes and apartments. And then we have to consider across the scale. We have to look at both local but also national and international. If somebody in another state is doing something that pollutes our water supply, let's say that we live in the city of St. Louis and we're taking our water supply from the Missouri River, if people up in Montana are doing things to contaminate the source of water, the Missouri River in this case, that impacts us. So when we talk about sustainability, we have to look at more than just our local scope. And all of this needs to be in an integrated fashion in terms of our management. We have to have goals. We have to have a coordination on the various levels of government and the private individuals and the end user. And we have to make sure these diverse stakeholders have insight and can help be part of the process for coming up with water resources development solutions. If we look at the challenges to sustainability, obviously urbanization is a big challenge. Pollution that goes along with that urbanization at times. We have droughts and floods, either too little or too much water. We have the impacts of climate change. If climate is changing over time and we've designed for a particular type of annual rainfall, but then the climate changes, either gets drier or wetter, we have to accommodate for that. There's the issues of population growth, not only accommodating the extra users, but also the stress that puts on the system in terms of quality of the water. And then we have an overconsumption of water. There are times when people waste water and overconsume for the resource that's available. Speaking of that, if you look at the western United States, which is dry, this is a map that was put together by the Department of the Interior that shows those areas where there's high conflicts high water conflicts are there's a high probability or potential for that. The areas in red show those kind of areas. You can see that on the western part of the United States in California. You can see along the Central Valley here, Sacramento South. And that's in the news lately with the droughts that they've got in California. This has been a problem in terms of water supply. Areas down in Arizona, Utah, New Mexico. You can see the front range of the Colorado, the Rockies here in the Denver. This front range is an area for high potential conflict. And then down in Texas, especially along the Rio Grande here, the border with Mexico, and then along the Gulf areas. Urbanization, basically if you think of the natural water cycle, that gets interrupted with urbanization. Either we don't allow water to naturally infiltrate and have water into the groundwater system where it can be recharged and used later as part of water withdrawal. You get the issues with wastewater that from people in their homes or for industrial purposes. You're putting a lot of water in a concentrated fashion out at a particular point in the watershed, which may not have good quality. And so we have to worry about wastewater treatment. We have to manage our stormwater because we have increased runoff. There's a number of issues with urbanization that create challenges to sustainability. For urban water management, we have both the water supply and the water excess management. We have our sources, transmission. We have to worry about treating the water. We have to have a distribution system to get it out to the end user, and then we have to have water collection and treatment, and then potentially we get reuse. In some cases now, especially in the arid West, you have reuse of that water that comes out of the wastewater treatment plants. They treat it to sufficient quality that they can reuse it almost immediately into various purposes. Then we have the water excess management, or the flood kind of situations. We have the collection and drainage systems. You know, you have to worry about getting the water out of points where you don't want it, conveying it off-site into areas which can handle that flood water. We have to sometimes treat it and store it and treat it, and so you have these retention ponds or basins that are created to hold that stormwater, which has higher incidences of oils and greases and other contaminants that you don't want to just release out in the streams. Now you have Clean Water Act regulations that are saying you have to take into consideration those kind of things and treat for those for a city to be permitted, and permitted that is from the standpoint of the U.S. Environmental Protection Agency permits and the state permits. And then you got flood control. You've got levees, dams, diversions, channels, especially on these larger rivers like the Mississippi and the Missouri, where we have annual flooding that you have to take care of. If you look at the water supply, there's an excellent example here in the San Francisco Bay Area. This is their just to the map, and you can see this is San Francisco Bay. This is San Francisco up in this area here on this peninsula. They actually get their drinking water from over 160 miles away in the Hetch Hetchy regional system, where this is Yosemite National Park, and you have actually capturing snowmelt runoff in the mountains, and they actually convey that into the Bay Area water supply. This is Palo Alto, San Jose, the Bay Area, all the way up into San Francisco. So, you know, there's this where we're actually withdrawing, and you see this a lot in the West. Los Angeles is another example where their water is actually coming from hundreds of miles away up in the mountains where it's snowmelt, and they're conveying it in there where they can consume it for their water supplies. This is another location. This is more of a excess stormwater component or excess water management issue. This is in Champaign, Urbana, Illinois, home of the University of Illinois. This is a project I actually worked on. This is called Boneyard Creek, and this is a highly urbanized area. And so we over the years, there's been significant flooding through the University of Illinois campus into an area called Campus Town, which is part of Champaign, where the students have various businesses that they can go and buy things, and restaurants and things like that. And so this is just sort of a map of the watershed here. This is the Boneyard Creek coming through the University of Illinois campus, and we set up, we had a long-term stream flow gauging station where we could monitor in a continuous form the stream flow, stage, and discharge, and then we put rain gauges around here to try to figure out what were the hydrologic characteristics of this, so then designs could be made to remediate for the flooding. This is an example of the Campus Town area in 1979. This is basically, you can see the flooded streets in the area, which cause problems. It's a very flat area, and you get these convective thunderstorms in the summertime, which can dump inches of rain and get a little problem with flooding. And so over time, they designed a system where they put in a series of pipes, enlarging pipes to have buried storage of the floodwaters. Plus, they also have large surface drainage systems or retention systems, which also captured some of the stormwater and stored it where it couldn't flood on downstream. And this is just an example of what's called the Healy Street Basin, where they basically excavated a large reservoir or large storage pit in the ground that could hold several thousand gallons and cubic feet of water for them to release later on. And this is what the final product looks like. And you can see that down here at the very bottom, this is in dry period. You've got a sort of a permanent little water thing here, which they're aerating to keep it from going anaerobic. Um, and then they also have, as I mentioned, they had some buried pipes that also provided additional storage and conveyance of the floodwaters. And this is sort of down on the University of Illinois campus after it was done. They basically had this is downstream of there. They basically redid the channel, makes it more aesthetically pleasing. Our USGS stream gauge is right here on the campus. You can see it in this building right here. Very, very nice location. All right, in all this sustainability issue, data is a key. We have to have data to be able to do any kind of assessment, planning and design, and to make that final risk awareness. And that data comes in various forms. Of course, we have the hydrologic data, which would be precipitation, and then we have stream flow, which we know the stage and the discharge, and we're going to talk more about that later on in the semester. But we need to know the flow rates of particular locations on the stream. And then we have to have information about the groundwater. What are the levels and how fast is the groundwater moving? Where is it moving to? Then we have data on water use. What are we using for water? What's the average residential use in a particular area? What's the industrial use? What's the agricultural use? What are we using and withdrawing for maybe irrigation? And then there's GIS, or Geographic Information Systems. We have to know something about the land use, about the topography, what's there in the built environment, what are the characteristics of the watershed in terms of its slope, its aspect ratio, how steep it is, and how it lays in terms of the prevailing weather conditions. Is the basin predominantly run west to east, and which would be with the prevailing storm conditions, or as the weather patterns move across? Those are the kind of things that are important data to help us with this assessment, planning, and design and risk awareness. Streamflow data, this is just a quick cartoon, and you'll see more about this in later lectures, but on this stream we would install a gauging station which would allow us to record autonomously what the level of the water is 24 hours a day, 7 days a week, and most of these are telemetered, where we basically broadcast that data back into a central office, and we would make discharge measurements, and we will actually make a discharge measurement on the river this semester. And we would make those flow measurements and come up with a rating curve, which would relate elevation or stage of the water surface to discharge. And through that, because we were measuring stage 24 hours a day, 7 days a week, we could use this rating curve to relate the stage to discharge and actually put out that data in real time to you as a private citizen or another agency, where we would have by date, you can actually see here what the flow rates are. If we assess the sustainability of our water resources, we have various ways to do that, and we do that through indicators or indices of water availability. We can do that looking at water budgets, how much is available for our use, and then what are we using. And if we look at having either too much or too little flow or water, we can look at probability of the stream flow or the flood probability. If we're maintaining our sustainability through increasing risk awareness, we've got to continually assess the water situation, because nothing is static. Part of that is looking at long-term data and trying to predict future trends. We also have the aspect of flood warning. If you are in an area which is prone to flooding, we can set up particular monitoring devices that would give you some sort of warning on the river itself. Weather Service puts out flash flood warnings. Whenever, if you don't have a particular gauge, you can just look at the conditions from the thunderstorms, see what kind of, rainfall rates they're getting, and issue flash flood warnings. For those places where we have streamflow gauges, they actually would put out a forecast for the flooding and tell you, so 3 days from now the flood's going to peak, or it's going to crest at a certain stage. So you're familiar with how you're aware of how quickly it's going to come up, how high it's going to get, whether you can make a decision whether you need to evacuate your home or make other kinds of arrangements. If we look at these indicators and indices, we have a hierarchy of these kind of indicators and indices. So if we look at just primary data, that's sort of the raw data coming in. And so primary data would be like the stage or water surface elevation. If we look at analyzed data, that would be turning that stage into sort of a flow rate, like in this case, a daily mean flow. And then it begins to get into indicators when I take that data and I do something with it. And so if I looked and analyzed the statistics and said, okay, if I have a lot of data here over time at a particular location, I can look and statistically say what is the 7-day low flow, or what are the lowest 7 days that I could expect on some frequency. Say on every 10 years, what would be the lowest flow for a 7-day continual period. That's something we would design wastewater treatment plants around, to be able to know what kind of flow that receiving water is going to be based at, because if you have higher flow, you can put out a flow of a lower quality and not do as much damage as you could if there's very little flow in a particular receiving stream, and you could do damage to the aquatic resource. The highest indicator or the highest of the hierarchy is the indice, which is basically taking an indicator and putting some sort of additional quantification in that, which would be, in this case, like water demand over the 7-day low flow, which would sort of give you an indicator of the stress index on a particular stream or water body. If I look at some specific indicators, one of those would be an example of like the normal annual precipitation. You can see here, this is long-term averages. Southern Missouri, in our area of Missouri, around Rolla, we're looking at 45 inches or so of annual precipitation. That would be what normally would have. Of course, there's fluctuations each year given dry and wet conditions. If I looked at 7-day annual or 7-day low flow, we look at those trends, and you can see, okay, what's been from the beginning of particular when data's been collected in a particular river, how has that changed every year? So you take the 7 lowest days of flow, 7 consecutive lowest days, and you plot that each year. And so let's just look at one here let's pick a site here. Pecatonica River at Freeport, Illinois. Look in the upper right, and you can see since 1930, you can see we've had a trend of increasing low flow. Whoop, let's go back to that. Increasing low flow. You pick another one, let's say over here in Bolivar, Tennessee, the Hatchie River. You can see again here we've got increasing 7-day low flow through time. As I mentioned, an indice such as the water stress index, it's based on human consumption and linked to population growth. If we look at a minimum requirement of 100 liters per person per day that's available to us, and agricultural industrial energy need is being 720 cubic meters per person per day. Okay, so if we add those two together and round up, we're looking at a minimum of 1,000 cubic meters per person a day to have sustainable low stress index for water. If you plot that around the world, these are the areas where we have the water stress. And so the warmer the color, the more water stress. That means we've got less than 500 cubic meters per person per year. And you can see, the desert Southwest, of the United States. You can see over here in the Arizona, the middle part of Africa and the desert areas, even certain parts of Europe and Asia. I'll just give you a second to look at that graphic, and you can look at where we've got water stress, and there's a lack of water stress where the bluer colors are where you've got sufficient water. Here's just another graphic of withdrawal as a percent of available water. This is another look at water stress in the sense of just kind of withdrawals and what we're using versus what's available. And obviously, if you use more than what's available over time, you're going to get into a deficit situation. So you can see those areas line up 1995 to 2025. You can see that if we continue in these trends, that we're going to have areas of water stress in the United States and Mexico. You can see they increase even into Asia and parts of Europe. If we look at water budgets, this is basically looking at what comes into the system and what goes out. And if we have precipitation as P, we've got surface flow out and in, we've got groundwater flow in and out, we've got evaporation, we've got transpiration, and we've got the change in storage. Transpiration is what gets basically consumed by the plants and put back into the atmosphere. And this is basically a simple water budget for a watershed. And you can look at this delta S here, the change in storage. That's what's in the system as storage, what's in there at any one particular amount of time. And so this is just a way of doing a water budget of a particular watershed. And obviously we don't have we've got the don't have the withdrawals and the uses that would be for anthropogenic or human uses, such as drinking water or for agriculture irrigation or for industry. This is basically what's coming into the system and what goes out from the natural hydrologic processes. If we look at risk analysis, and again, this lecture, I'm just kind of giving you an overview of various topics that we're going to go through as part of the class. If we look at risk analysis, we've got risk from flooding, we've got risk from droughts, we've got risk just from the flow conditions of knowing what's out there, what we would expect to have in terms of if we wanted to withdraw water or we wanted to put wastewater effluent into a particular situation, a particular stream, we'd have to know what the probability of particular flows were going to be. When we talk about flood probability analysis, we're not going to get into much detail in this class. There's a chapter in your textbook in Mays that deals with this, but it's basically a statistical procedure to determine probability that a given flow will occur or be exceeded. And when we talk about the 100-year flood, that's what we're talking about, is we've done a statistical analysis of a particular location and saying, okay, we have a 1% chance, that's what the 100-year flood is, 1 over 100 is 1%, or 0.01 probability of having that flood in any particular given year. Of course, there's some assumptions as to the distribution of the probability, and there's some underlying things there. It's a subject that requires more than just a simple slide or two to really understand, but it's something that we would look at in terms of on an annual peak flow series. This is the annual peak flows for Grand Forks, North Dakota on the Red River. And so these are the floods, the biggest flood in any given year, and they're plotted here. And so we would do a statistical analysis of this and come up with a probability distribution that would basically predict, here's the 1% chance flood, which is the 100-year flood. And we'd go up and look at this probability distribution that we fit through the data, and we come up and say, okay, well, this is in log scale over here. So this is 1 times 10 to the 4th is right there. So we would go up and say, all right, this is 10,000. Here's 1 times 10 to the 5th, which is 100,000. So we're looking at the 1% chance flood is 2, 3, 4, 5, 6, about 70,000 CFS here, cubic feet per second. You can talk, as I mentioned already, that Chapter 10 discusses this probability analysis for flooding. It goes into more detail. I'm not going to go into a lot of detail more in this class. We will have a couple discussions on flooding and flood probability later on, much later on in the class toward the end of the semester, but won't go into great detail on how we would do a flood probability analysis. This is looking at risk analysis from droughts, and this is the U.S. Drought Monitor. And the colors here, the warmer colors, this is August 7, 2012, and you can see that we were in a extreme or exceptional drought. This is back in 2012 when it was very dry in Missouri and northern Arkansas. This is put out every week by the U.S. Department of Agriculture, and you can see this if you are interested in what we've got going on right now. You can go to this website here, and just gives you an assessment of when we have, where the drought conditions are around the United States at any given time. This is looking at stream flow. This is put out by USGS. This is the areas in the warmer colors. That's where we've got lower than normal stream flow for that particular day. This again is August 15th, 2012, and that corresponds, you can see back with the Drought Monitor where we had the red, dark red colors. That's also where we have the low flows, where it's abnormally dry in terms of our stream flow. This is a flow duration curve, and we'll talk a little bit more about this, but basically this is plotting stream flow on a particular location, looking at the probability of occurrence. And so if I've got 100% probability of occurrence, that means all the flows in that data set are greater than that particular flow. And so this is log cycle, log scale here. So this is 1 cubic feet per second, 10, 100, 1,000, 10,000, and you can see how the data plots. And we'll talk a little bit more about how to get that, and that'll be in some of your notes from your water resources concepts. And so we basically look at all the data and we order that from largest to, or smallest to largest, and we come up with a probability plotting position, and we'll talk a little bit more about that later. Okay, we use those flow duration curves to not only assess the current conditions, but also estimate stream flow at ungauged sites, estimate the in-stream stream flow needs for a particular habitat. You know, the biologists and the environmental engineers use flow duration curves a lot to be able to make assessments onto what is the hydrology of a particular stream, and a flow duration curve is a quick way to get a feel for what that hydrology for that particular stream is. I'm going to skip over this. This is basically the hydrologic unit codes, or HUCs. This is all the stream watersheds in the country are based into these various hydrologic unit codes. You can just see them there, all the different watersheds around the United States. And by those codes, we also have indicators on this Water Watch web page that USGS puts out. This takes the streamflow data and puts it out by hydrologic unit code. So you can see the areas. Again, this is the August 2012. You can see those areas, what the watersheds look like that are under stress from